Hello, everyone. My name is Alina Bonadonna, and today I will be a moderator of our another amazing webinar session. And I'm super happy to welcome here John Donaghy, Global Head of Food Safety at Nestlé. Hi, John.
Good morning, Alina, or good
How
afternoon,
are
sorry.
you?
Yeah, I'm very good, thank you.
Good, good. And guys, if you see us well, hear us well, please either react on this beautiful small like emoji icon on the bottom left, or just drop a few pluses in the question window that you hear us well, see as well, so we can go on. Amazing. I already see some first reactions are coming. And guys, don't hesitate to shoot on John your amazing reaction, so he will be more inspired to share more insights. Where are you based now, John, by the way?
No, I'm in Switzerland. I'm just back from Dubai last week, so I gave a few presentations last week on topics different from microbiology, mostly on big data. So that was at the Dubai International meeting last week. So I'm glad to get back to Switzerland for a week before my next travels.
Great. And guys, where are you from? Also drop us here. We are really curious because I know that we have quite amazing international community. And thank you all for coming to our academy session. And another thank to Nemis Technologies for supporting this project. Okay, nice. So people are coming from France. There is a Jerome Combrisson saying hi to you, John. Probably you know him.
Yeah.
Yeah, definitely. So, guys, don't hesitate also to drop in the trickiest question after the presentation. John will answer it. And John, if you are ready, I'm just sharing the screen straight away.
Okay.
Ready? Good.
Yes, no, ready when you are. I apologize because we had some difficulties with our cyber security. Clearly, Nestle's cyber security is very intense. So with the GoTo webinar platform, we had difficulties for me to be able to manipulate the screen myself. So Elena at Nemes will be manipulating the screen. She'll be my remote control for the next 30 or 40 minutes. So hopefully that goes okay. So I'll give you the prompt, Alina, when I want to move. Okay.
Definitely. And I will switch off my camera so everyone will see you, John, perfectly.
Mhm.
And we are ready to start. Okay. Zooming in
Okay.
presentation and let's go.
Okay. So thank you all very much for joining this webinar. I believe from Elena, there's 200 to 300 people at least have registered. So thanks for joining. And maybe it's a cryptic title of my slide that encouraged people to join to find out what I want to talk about. And as the title suggests, I'm talking about old age pathogens. So pathogens that have been around for a long time, a bit like myself, finding new homes where we see new vehicles of transmission in terms of outbreak cases. Next slide, Elena. Okay, so my talk will really focus on three different aspects. I would say fairly related aspects, but some differences. Firstly, I will contend that really the pathogens that we have seen over the years, and when I say over the years, I mean over the last 50 years, even 100 years, has not changed a great deal. There is no brand new pathogen that suddenly appeared on the scene, but what really has changed has been the vehicles of transmission. If you look back at some of the foods that some of the pathogens have been found in over, say, 50, 60 years ago, compared to some of the foods that they're being found in now, and some of the outbreaks associated with certain foods, you'll see that the old pathogens are still around, but they're actually finding new homes or new foods. And one of the new foods we've seen pop up recently has been the shift towards plant-based diets. So plant-based foods away from animal-based foods, although animal-based foods are still predominant. And again, moving to plant-based diets, let's say, and consuming plant-based foods, also comes with food safety risks and food quality risks. So I'll delve a little bit into what those can be as well. And then something that really has changed quite a bit over the last 20 years has been microbiological analytics, and in particular diagnostic methods. Not only diagnostic methods, but also methods of investigation like next generation sequencing. So at the end of my talk, I'll talk a little bit on analytics and how that has come along in the last 10 to 20 years. So what I want to do now over the next few slides is actually take you through a few traditional pathogens that we know of, and then see how the landscape has changed. So if you go to the next slide. Okay, so this is what I would call the rogues gallery of pathogens, for example. So you will see in the bottom left hand side of this some some of the pathogens that have been around for a long time. You can see Salmonella was around from the early 1900s. You see even Clostridium botulinum was around then as well. And you look at this through the last 100 years, through the last 50 years, you'll see some of these pathogens are still the cause of foodborne illness and foodborne outbreaks even to this day. Some of them are less prevalent because we've intervened in terms of, I would say, our processing activities. For example, Mycobacterium tuberculosis has virtually disappeared as a foodborne pathogen because we've introduced pasteurization for milk, and this is one of the major transmission vehicles. Also, things like Brucella as a foodborne illness has also sort of virtually disappeared. So, as we develop new processing technologies, we tend to eliminate some of these older pathogens. But then again, sometimes changes in processing can bring about let's say newer pathogens or changes in pathogens. And if I look on the right hand side, for example, you'll see around the 1980s, 1990s, we start to see the emergence of Listeria, Campylobacter, E. coli, etc., and Chronobacter. If you look at Campylobacter jejuni, as you say, it was never really heard of much before the 1970s. But since, let's say, the intensification of poultry farming, you could almost draw a correlation with that and the emergence of Campylobacter as a foodborne pathogen. And now you see it's responsible for a very large number of sporadic outbreaks, globally, especially in Western countries that consume poultry. Again, with Listeria, you might point to the introduction of the chill chain, for example, and we know Listeria is an organism that can actually grow and likes chilled conditions, and you might say it began to emerge alongside the chill chain, for example. Then Aztec E. coli, again, we saw its emergence probably for the first time in the Jack in the Box outbreak in 1993 in the US, associated with meat. And again, now it's a very common pathogen, but as I will show later, it's now spread to other vehicles of transmission, not just meat. So you see, when you look at this rogues gallery of pathogens, not an awful lot has changed over the last 50 to 100 years in terms of which pathogens are still around. But I will contend, as I said, that they are finding new homes or new vehicles of transmission. So if I take a look at Salmonella as an example, when I was a young graduate and doing my PhD, the main thing of concern in Salmonella was eggs. And eggs and also milk powder. So really low moisture products, for example. But then with eggs, especially in the UK, they start the vaccination program, and so salmonella in poultry became a bit less of an issue. But we still saw it appearing in low moisture foods. For example, in the 1980s, 90s, there was salmonella issues related to chocolate, for example, a low moisture product, and that really has not gone away. If you look in the last 2 to 3 years, well, again, we've seen it popping up in things like peanut butter, again in chocolate. So salmonella is still there. Low moisture foods are a big risk for salmonella. But we've seen it appearing in some, let's say, new vehicles. Tomatoes, for example, which is something we may not have considered previously as a vehicle of transmission for salmonella. But as people have, let's say, modified and bred different forms of tomatoes, for example, that there may be a lower pH, then salmonella can actually survive better in some of these foods. We've seen it appear in some snack foods, and this is where, for example, you are adding spices, herbs, etc., as a critical material, as a dry mix material to like fried chips. Another common one, which we've seen over the last, probably the last 2 years, is things like humus, sesame seed, etc. There's been a large number of outbreaks and cases related to, again, another low moisture food, but it's something that's actually more consumed now than previously. So that's probably why it's been highlighted. We also see it associated with, for example, pet food, salmonella. And again, pet food, salmonella can cause illness in the pets themselves, but also we know that kids can actually get cross contamination from pet food that's on the floors, etc. So if you look on the right hand side of this slide, you can see salmonella, the old pathogen, like previously associated with low moisture products like milk powders and egg, for example, has now sort of appearing in these new vehicles. If I then look at Listeria monocytogenes, as I mentioned before, the introduction of the chill chain probably led to the sort of the elaboration of Listeria monocytogenes and those sort of chilled and frozen type products. But it was traditionally associated with deli hams, soft cheeses, etc. Again, when I was a graduate, the thing you always learned was that Listeria monocytogenes and the risk of it being a teratogenic agent, i.e., leading to abortions in pregnant mothers, was a high risk. And they always warned mothers not to consume low moisture cheeses, etc., because this was a common source of Listeria monocytogenes. And the deli ham issue never really disappeared. We saw in recent years the large polony outbreak in South Africa, which led to over 1,000 sort of cases. And we saw other outbreaks related to, again, deli ham, for example, in Spain in 2019. And we saw sandwiches, again, being implicated in an outbreak in the UK related to the meat a couple of years ago. And we saw it also in frozen products, products that were meant to be non-ready to eat, but they were misused in some way or other. And again, they were present in frozen corn. So some of those are what I call the traditional vehicles of Listeria monocytogenes. But again, new vehicles have appeared. We've seen, particularly in the US, we've seen a number of outbreaks related to cantaloupes, melons, etc. We've seen, for example, also with broccoli associated with Listeria monocytogenes. And we had the rare case of Listeria monocytogenes illness caused by what we call toffee apples. So this is where apples that are actually coated in a sugar-like material, and it was purported that we had Listeria growth at the interface between the sugar and the apple itself. And we've even seen it, quite unusually being associated with some cases and some recalls in low moisture products like sunflower seeds, like nuts, and even like a low moisture snack type materials like muffins. So again, you look from the left hand side, the traditional vehicles, deli ham, raw cheeses, and now you find it in many different sources. And maybe this is a result of the types of products that people are eating. And as I will show later, maybe it's because the detection methods and diagnostic methods and methods of investigation are much better than they were before. So we move to the next old pathogen, let's say, and that is S.A or Shiga toxin producing E. coli. So I'm not sure which. I think we should be further on in the slides, Alina.
Mm-hmm.
Sorry, I
Yes.
didn't maybe. Sorry, I didn't maybe. Okay, sorry about this. So if you move to the S.A, so this was sorry, this was I didn't tell you to move, so sorry.
It's okay. So here is the salmonella and
That's
then
the
listed.
salmonella and the new vehicles. Sorry. Listeria, the old style vehicles, deli ham, new vehicles, these plant-based products like broccoli, cantaloupe, melon, honey apples. Now we move. Now we've caught up. Okay. So again, you look at Shiga toxin producing E. coli. As I mentioned before, the big outbreak was Jack in the Box back in 1993, related to burger patties, and again, it was also associated with raw milk cheeses. And we had the fenugreek seeds in 2011 with the German outbreak. So these were, the German outbreak resulting from fenugreek seeds led actually to introduction of EU legislation. But up to that point, still meat was viewed as probably the major contributing factor to STEC foodborne illness. But if we look down the last 5 to 10 years, We've seen more and more cases related to fresh produce, especially in the US and also in Europe. And we've seen many cases related to lettuce, romaine lettuce, and this has been linked back to irrigation water or animal ingress in fields. We have also seen wheat flour as being now a vehicle of concern as well. So again, it ends up in cross contamination in the fields, resulting from either adverse weather conditions, runoff from agricultural land, etc., and wheat can get contaminated and ends up actually in the flour. And we've just seen just last week the case in the US relating to slithered onions. So again, another case of a new a relatively new source of S-Tech. So we've moved away from, let's say, the left-hand side of this slide, meat being the predominant vehicle of transmission, and meat and minced meat and burgers being the common cause of many illnesses. To on the right hand side, we see as more and more perhaps consumers consume more and more of the products on the right hand side, then we see more of these outbreaks. So we've seen that with S-Tech, just like we saw for Listeria and we saw for Salmonella. And if we go to the next slide, it's not isolated to the bacterial pathogens, for example. We've seen the same thing in norovirus and Hep A. These are enteric viruses, so viruses that can cause foodborne illnesses. We know viruses cannot grow on food, so generally they have to be result from a spot contamination or cross contamination, again, perhaps from water. But we look back when noroviruses were hitting the headlines, it's generally associated with water, it's generally associated with cruise ships and person-to-person transmission, for example. We did see some cases related to shellfish and also lettuce as well, back in probably the 1980s, 1990s. So these products are still vulnerable to norovirus and hepatitis A enteric viruses. And but then the new vehicles related to norovirus hepatitis has come on the scene more recently, and we've seen many outbreaks related to frozen berries, for example, also related to mangoes. So these are very different vehicles compared to what was traditionally associated with hepatitis A and norovirus with the berries, etc. So now that I've shown you next slide, sorry, I've shown you a few examples of where I consider that the pathogens have stayed the same. So Salmonella, Listeria, S-Tech, enteric viruses like norovirus and hepatitis A. I've demonstrated that they are not only found in the traditional transmission food vehicles, but also been found in other sort of what we'd say rare food forms. But one of the big changes we've seen in recent years has been the move to plant-based diets, and that was with plant-based meals. And this in itself can present some risks for food safety and food quality. And where we've seen the shift has been on what I see on the left-hand side has been the move from meat to meat analogs. So this is the replacement of meat protein, pork, chicken, beef, etc., being replaced by the likes of soya, pea, etc. And then on the beverage side, we've seen a big switch from dairy-based, animal dairy-based beverages to the likes of almond, oat, coconut, pea as beverages. So what you might ask, what new risks do these present? Well, again, you look at the types of products that. Next slide, please. If you look at the types of products that we see produced, you will see on the left hand side you have replacements or substitutes for tuna, called for shrimp. You've seen the meat burgers being replaced by pea or soya based burgers, etc., etc. And you'll see there's been quite a few publications, what you see in the middle here, that actually talks about the different food safety risks. And those food safety risks exist because this is a different raw material compared to typical animal-based foods. We understand what sort of pathogens can be transmitted through animal-based protein, for example, through abattoirs and processing, etc. But here we're talking about an entirely different type of matrix. So do we really understand the microbial ecology of these raw materials, the likes of soya, the likes of pea, the likes of oat, etc.? And then how do we design the product? Typically, we knew how to design meat-based products in terms of limiting the growth. For example, listeria. If I if I develop a product that is supposed to be a listeria no growth product, we sort of know the solutions and how to do hurdle design in terms of these sort of products. But do we know the same for a plant-based product? I'm not so sure. Some of the models that have been developed to actually design safe plant-based products, are not necessarily suitable for plant-based products. So we have to look at different challenge tests to understand, how we actually design safety into these products with regards to some of the foodborne pathogens. Also, even simple things like the validation of cooking instructions. How do we need to do that separately? We just can't extrapolate direct from meat-based products to plant-based products. So that's really on the meat analogs. If we go to uh, the next slide, you will actually see on this next slide that there has already been some recalls and outbreaks related to some of the well-known plant-based substitutes. For example, fava beans is a well-known replacement for some of them in the meat-based products, and we've seen some listeria outbreaks. So we still have to handle listeria, just as we would for meat and deli type products when we design products that contain some of these novel proteins. See, we've also seen salmonella issues in relation to pea-based protein. And then, of course, with the alternative proteins, for example, insect proteins, and there's very interesting reports produced by the FAO that actually talks about the food safety risks associated with these novel protein sources such as insects. So again, as we switch to these new foodstuffs, we still have to be aware of the old pathogens that still could be a factor in terms of a risk as we design new products containing these proteins. If you go to the next slide, and this relates more to the beverage. So when we talk about beverage and plant-based, as I mentioned before, this tends to be replacing milk, let's say, as a dairy ingredient with alternatives such as coconut, oat, soya, pea milk, etc., rice milk. So all of these, as you see on the right-hand side, come with different issues and how you have to manage food safety, and in this case, more quality, because it's a lot of it relates to spoilage. Because a lot of these beverages will be produced by either by retorting, by UHT, hot fill, etc. But again, they come with their own problems. We know how to manage milk. We know how to cool milk. We know how to mix and dissolve milk powder. Do the same rules apply for some of these other let's say ingredients? If, for example, you cool down coconut milk, is it easy to push through pipes? Is it easy to clean as dairy based? These are all new challenges that come as we switch, from dairy based, to these dairy alternatives. And again, we have to think: is there models available for predicting growth, predicting inactivation in these novel plant-based ingredients? So they do come with challenges, the plant-based, and they come with challenges for safety, but also challenges for quality, in particular for spoilage. And again, there's been some recalls related to spoilage and quality defects in these alternative dairy-based beverages. So that sort of highlights a little bit, as the consumer changes habits, we as food safety microbiologists have to think of what new risks might these bring about. Most likely, we will still consider the exact same pathogens that we considered for other types of like meat-based products, etc. But they will come with new challenges. The next part that really has changed has been microbiology. Sorry, if we go to the next slide, Alina, I keep forgetting. Has been microbiological methods. So a lot has changed since the invention, let's say, of PCR in about the 1980s. So we've moved away a lot from culture-based methods on the left-hand side, which are slow, let's say, and laborious, to PCR-based diagnostic methods, which are much faster, require some more infrastructure and competence, but nevertheless, these are widely used. And in between, we probably have the immunoassay ELISA-based methods. So, and again, laboratories use a variety of these three, but the shift is mostly towards the ELISA-based methods or the PCR-based methods. So really, we've seen a rapid an emergence of these rapid methods. But where the big change has taken place has been investigative microbiology, and this is next generation sequencing. And the two components of this has been the use of whole genome sequencing, and secondly, the use of metagenomics for, let's say, more ecological studies. If you go to the next page or next slide. So these new forensic tools can be really divided in two. Whole genome sequencing still depends on culture. To do whole genome sequencing, we need to isolate a culture from whatever matrix we're investigating, be it environmental swabs, be it finished products, or be it raw materials. So we have to get a culture, and then we look at its DNA makeup, and we compare the DNA makeup of one isolate compared to another by whole genome sequencing. On the other hand, you have metagenomics, and this is where you just take all of the DNA out of a sample and you look at the relative abundance of that DNA, and it has its own uses as well, which I will come to. So if you go to the next slide. Whole genome sequencing really is now the tool of choice for source tracking or source attribution. Every foodborne outbreak almost since about 2011, 2012 is now investigated using whole genome sequencing as a means of source tracking. So very isolated incidents, even over, let's say, a geographical span or even a time span can be related. I show a couple of examples down the middle here where there's been almost 10 years between the first isolation and the next isolation, and links can be made clearly by whole genome sequencing, where the same isolate has been in the same plant or over a long period of time and can lead to foodborne illness, 10 years apart. So whole genome sequencing is a way in which now helps with this sort of a root cause analysis and helps with this sort of source tracking. And to match that, there is what we call the Genome Tracker database, and this is housed by the FDA in the US. And this is basically a large database of pathogen sequences, and many laboratories from around the world contribute to this database. There's something like almost 2 million isolates in this database at the moment, in the Genome Tracker. So if you're in the US and there is an illness and there's an isolate from a patient, it can be actually put into this database and tracked to see if this isolate has been isolated before and what type of food it was associated with. So this is a very powerful database, the Genome Tracker. But even for industry, this is an extremely useful tool in terms of root cause analysis, where, did your isolate that you may find in your environment, did it come from a raw material? Was it a persistent strain? Was it a transient strain, etc.? So it is really an extremely useful tool. Metagenomics, on the other hand, and whole genome sequencing is now quite mature. Sorry, if you go to the next slide. So whole genome sequencing is quite mature. The pipelines and the process and ways of working is quite now well established. However, metagenomics is probably the new kid on the block, and it's less established, I would say. Remember, I said it's all about extracting the DNA from any sample and then looking at the relative abundance. So the typical graph you'll see for metagenomics is something like on the right-hand side. You'll see the relative abundance of the DNA of different organisms in that particular sample. So it can give you, it's a culture-independent method. It can give you a taxonomic picture of the microbial community of whatever you test for. So if, for example, you do this on a raw material, for example, fresh milk, you might say, okay, this is what fresh milk normally looks like. So then if I use this on a general basis, I can see how my fresh milk varies by season based on the microbial composition, or maybe how it varies from farm to farm, or if I see any abnormality. I can also do the same for my processing environment, for example, and you can establish an ecological study for your processing environment based on swabs or whatever. So this is extremely useful from an ecological point of view, but it's still, I say, fairly fresh in terms of how it is used. It can be used, and we have used this as a diagnostic tool for spoilage, and I'll show you an example just shortly. If you go to the next slide. So on the left-hand side are some of the parameters we can look at. So if you want to see how did my cleaning schedule change, how did the seasonality of my raw materials change, how have I done some interference with a particular, cleaned the floor with a certain, disinfectant, cleaned a piece of equipment with disinfectant, left the equipment to run for a longer run time. I can do a sort of a microbial ecology and look to see what is the distribution, how does it change over time. So this can actually give you a good hint of let's say the microbial ecology of the factory. What you see in the middle here is a metagenomic study of two different factories. The one in the blue, one in the red. You can see clearly the one in the blue has a much richer and a more widespread microflora. Every dot is a different sampling point. This can be the difficult with metagenomics. Each sampling point can give you quite a different profile, but you can see in general terms what your factory ecology will look like at certain sampling points, and then you can see the impact of certain treatments like cleaning, for example. Where it can be useful metagenomics, and as we have shown it to be very important, is in spoilage. If, for example, you have a spoilage event, and quite often with a spoilage event, you cannot detect which organism is actually sorry, sorry, it's okay. You cannot detect which organism is present because the organism may have autolyzed, and you do it as streaking onto plates, and you can't see anything, but you know your product is spoiled. If you do whole genome or sorry, if you do metagenomics, so you extract all of the DNA from that sample, then you will be able to see what is the relative abundance of the various organisms. And the organism that has caused the spoilage will probably be the most abundant organism. Then you can actually see, was that spoilage organism present in my raw material? Was it present in my factory environment, etc.? So it is proven to be a good tool, metagenomics, for diagnostic spoilage. So this is, but as I say, it's relatively in its infancy, metagenomics, as a sort of a food industry operational tool, and it is less mature than whole genome sequencing. So just in summary, and this is you go to my last slide, Elena. So what I can say is, as a summary, the same old pathogens dominate foodborne illness, and even if you look at some of the ECDC, the European reporting system, you'll see, and you look at the foodborne pathogen data from any year, you'll still see the usual culprits there. You don't see a lot of new emerging pathogens. You'll see the same ones dominate foodborne illnesses. The vehicles of transmission, hopefully, which I've demonstrated to you for Salmonella, Listeria, STEC, for viruses, are forever changing. Where we are finding and seeing foodborne illness, foodborne outbreaks now, are in new foods that were not the focus of attention probably 30, 40 years ago for some of the traditional pathogens. And maybe that is because our methods are getting better, at detecting and making a correlation between, or a relationship between, some of these foodborne outbreaks or these foodborne cases. Whole genome sequencing is adding greatly to that, and it's revolutionizing source attribution or source tracking, as the governments would call it. Metagenomics will also add valuable information in the future with regards to the microbial ecology of our raw materials, our factory environment, and our finished products. And for sure, this is going to tell us a lot more of what is there, and it may actually uncover new pathogens. So in the future, because we will be looking at the DNA that isn't present in many samples. So this may be a route to uncover new pathogens of the future metagenomics. So that is my final slide, and I'm happy to take any questions, Alina, if there are any.
Definitely, I'm sure that there are already some questions. Yeah, I see it. And honestly, guys, uh, crazy.
Yeah,
So there
I,
is the
I'm sorry
biggest.
about I missed the slide turning at the beginning. That's the difficulty with our cybersecurity and me having to join in this particular way.
Yeah, okay. The first question comes from Jeff Banks. Hi, Jeff. Hope you enjoyed the presentation as well. It was also one of my speaker, and if I'm not mistaken, we discussed a root cause analysis. So, Jeff asked, you mentioned outbreaks and recalls for Salmonella in hummus. What specifically is the root cause of the salmonella contamination in sesame seeds, and what is interventions would you suggest?
Yeah, it's a good question because humus is just like chocolate and some of the other low moisture foods is a food that's actually very difficult to treat, from a thermal processing perspective. We see salmonella, coming in seeds now, so it must, where it originates from, is a good question. But we do see it in these raw materials like sesame seed. But when sesame seed are ground and then they are meant to be heat treated, this is quite a challenge, is to do a sufficient heat treatment to kill the salmonella. And then this is where it ends up in some of these low moisture foods, or it may be a result of cross contamination at a plant where you get, if the zoning is not done properly, etc. But the intervention, the thermal processing is probably the best intervention that we know. As as regards, let's say, a critical control point for the treatment of salmonella and these low moisture foods, but we know it is challenging. But there's all the other prerequisite programs which have to be taken care of. So really, from the good agricultural practice right through to you know things like hygienic engineering, cleaning and sanitation, etc., etc. And Jeff understands what these are.
100%. Thank you, John. And next question, actually, two questions came at the same time from Matis Kamps. And I will start with the first one. Do you have advice on establishing microbiological limits for a new plant-based product? Both what parameters to analyze and up to what limits are acceptable is the first one.
Well, in a lot of legislation, there is generic legislation set for ready-to-eat foods. So that's probably a good starting point. What is your regulatory limits? We know sometimes different countries have different approaches to setting limits. Sometimes they will have a horizontal approach like Europe, or they will have a specific commodity-based approach. And that is probably, what should be a starting point, and is probably the same regardless of whether it's plant-based or whether it's non-plant-based. So when we think of chilled and frozen products, Listeria monocytogenes will be as relevant for a plant-based burger as it will be for an animal-based burger, let's say. So many of the food safety criteria that are set, when we think of food safety criteria, we think of the pathogens. So, probably the salmonellas and then the listeria for chilled and frozen foods. And then you have the process hygiene indicator. So you'll have your EBs, you'll have your total count, you'll have Bacillus cereus, Staph aureus, and then depending on the nature of the material and depending on what type of product you produce. So if it's a UHT product, obviously that's very different compared to something that's a ready-to-eat, chilled and frozen product. But let's say the regulations will be more or less the same. You have to address it specifically, depending on the type of material you're producing, depending on the process that's being used. A UHT, which should be let's say a commercially sterile product, is very different compared to a ready-to-eat chilled and frozen.
Okay, the second question is to what extent may we rely on the microbiological limits for the original animal-based products?
Um, I would say it can be used as an indicator, but it should not be a direct extrapolation. If I give maybe an example to demonstrate my point, if I take uh, rice cream, okay, so there's a product called rice cream, basically, which is like ice cream, but made with rice milk. So rice, we know, has a higher than normal prevalence of Bacillus cereus because of the way it's growing in paddy fields, etc. So in that case, Bacillus cereus will be a lot more relevant, compared to, let's say, maybe animal-based, milk products. So in that case, you would have to consider, how it is processed and what the risks are for Bacillus cereus. So it's not a direct, direct correlation in terms of the parameters, or sorry, in terms of the limits. Some of the organisms will be the same organisms will be of concern, I would imagine, but sometimes the limits may actually vary depending on the raw materials. If you're worried about spore formers, Bacillus cereus, etc., depending on the process you use, then it would be a good idea to have maybe adding different limits for those sort of raw materials.
Thank you, John. And I just want to remind all attendees that to ask questions, you just need to drop it into the small question field. And unfortunately, the current format are not allowing you guys to speak, but probably the next webinars we will do as a panel discussion with more interaction. But still, we have more questions coming, and the next one is from Carmela Pinakia. I see the potential of metagenomics, but I think it's still a quite expensive investigation and probably not many factories know about it or can afford it. How do you see the practical application of these kind of studies?
Yeah, no, the questioner is exactly right. Metagenomics, just like whole genome sequencing, is not a cheap tool either, but you have to weigh the risks and the benefits. So there is obvious benefits for whole genome sequencing, which helps with your source tracking in your factory. If you can identify a root cause very early and diagnose an issue you have, then of course that has great benefits. Metagenomics, probably less so at the moment. I mentioned one example where it can be very useful for diagnostic of spoilage, where you're unable to culture an organism and you want to understand which organism caused your spoilage, but you can't isolate it. So in that case, metagenomics is clearly a very useful diagnostic tool, probably as a one-off rather than as a sort of a regular operational use. Um, you're right that it is more used as a, let's say, as an R&D tool at the moment to understand factory microbial ecology, because it's almost like in chemistry we often talk about having non-targeted screening methods, and this is something that gives you a profile and then you can see where something has changed. Metagenomics could potentially be used, for example, on certain commodities. So as I mentioned, you're buying in milk, for example, and milk has a certain metagenomic profile based on the DNA, based on the organisms that are there. And generally, if you look at milk, you will see the same organisms, if it's bovine milk all of the time. But what, for example, if that milk was adulterated or abused with antibiotics, would that microflora change? So I'm speculating about maybe in the future how it might be used. So you can do quick metagenomics. Well, it's never going to be quick, or at this moment in time, metagenomics is not quick. But you imagine you had a way of doing metagenomics faster that could be used as a screening method for some of your commodities. So you could immediately spot that, okay, there's a change in my microflora. Why did that change? So, and this is where I see it going in the future, or I get a change in my, I'm doing cleaning on my line. I know what my surfaces should look like, or whatever, and then suddenly I see, look, my cleaning has stopped working the way it used to because I'm starting to see a different microflora present after cleaning, or maybe post sanitation. So let's say this is where they use it from a clinical setting. When people talk about clinical microbiome in the gut, they look at people who have a diseased gut versus someone who has a healthy gut, and they look at the microflora by almost like metagenomics, so they can make comparisons between, let's say, good and bad. And that would be the idea in a factory, that we could actually sort of have these patterns, so we actually can, it gives us a quick indication that something has gone wrong or something has changed. But I agree, it's probably further down the line, and I'm talking maybe 5 to 10 years, to be able to use as a routine tool, for this sort of rapid type of results.
Thank you, John. The next question is from Madhu Pillai. Recent incidents on Listeria and E. coli O157 are becoming more common than Salmonella contamination these days in the US. Is there any specific reason for the same?
Yes, a bit of a speculative question. You know, it is. Well, I don't know. I cannot, let's say, comment on the statistics that there's more outbreaks. Yes, there seems to be more outbreaks on fresh produce in the U.S. over the last number of years. That is for sure. And a lot of those outbreaks have been linked to leafy greens, lettuce, etc., romaine lettuce that have been grown in certain areas. And when whole genome sequencing has been performed, a lot of the source attribution links back to irrigation, runoff from farms, etc. So maybe you could speculate that maybe there is more consumption of that type of product than ever before, and then with the tools like whole genome sequencing, it is actually able to link isolated cases which in the past were never able to be isolated. So it's a little bit speculation, what it could be. Maybe it's a combination, increased exposure because of increased consumption as people maybe move to, more leafy green, type of diets and consume a lot more of it. And it could be also related to the fact that with whole genome sequencing, we're seeing individual cases that probably 5, 10 years ago we never would have seen because of we didn't have the tools like whole genome sequencing.
Thank you, John.
Whether it's greater than salmonella, I couldn't comment. We still see foodborne outbreaks of salmonella, in the U.S. In fact, we see the recent one with regards S.A in onions. We have seen salmonella in onions in the last few years as well. So you could argue that that type of products or some of these agriculturally growing products are vulnerable to any of those pathogens, be it S.A or salmonella.
Yeah, definitely. And we are running out of time, but not running out of question, I should say. So the next is coming from Jerome Comberson. Do we lack microbial growth modeling in the new type of food? And do we need more research on cardiac parameter in these new food matrices?
Simple answer to Jerome, yes. Yes, we are lacking, let's say, the models that we have, and this is what we discover as we move to plant-based product design. The models that we have, like the traditional models, FSSP, Combase, Simprevious, etc., when we try to, let's say, replace challenge tests with modeling, then we suddenly say, well, we're not sure because of that matrix, because it's a different matrix compared to what the models have been built around. So you end up actually doing more challenge tests because of these new matrices, and uh, and hopefully then as more challenge tests are done, more data will go into these models, and then the models will become better. But for sure, the models as they existed, probably should not be used blindly as they were for animal-based protein type foods. So, but hopefully, as now more and more companies are producing more plant-based foods, that the models will get richer in the future. And as Jerome has said, the cardinal values for some of these pathogens in these plant-based foods will become more prevalent, and we'll have a lot more data in our databases around this.
Yeah, thank you. The next question from Lavanya Nidunapu. What would be your suggestion while preparing the hazard analysis as the prevalence of these old age pathogens is no more the same? It's more for food service business, the question.
Yeah, and when you do your hazard analysis as part of your HACCP study, the key thing is looking at the intrinsic risk of your raw materials. And in a lot of cases, some of that is based on expert elicitation, and that expert elicitation is based on surveillance, it's based on outbreaks, etc., etc. So these new vehicles, as I call them, have to be part of that hazard analysis. Traditionally, yes, you would have known. I always say there's a lot of pathogen product combinations. Eggs, salmonella, chicken meal, chicken powder, salmonella, low moisture dairy, salmonella. You know, raw milk cheeses. You can make these pairs. You can pair a pathogen in a product, quite easily. But now we have to think differently, because now if you are, for example, looking at leafy greens, for example, you look at these agricultural-based products. You have to think, okay, what pathogens could be associated with those, and how do we mitigate the risk? So this is something which I would say is you have to bring to bear as part of your hazard analysis. It's the intrinsic risk associated with that particular foodstuff, and it's not the traditional foodstuffs anymore because of what we see in the outbreak cases. So these agriculturally grown products now, and it's a challenge. These are grown in the field where you'll have irrigation water, you'll have water canals, you'll have ingress from domestic animals, you'll have runoff, you'll have climate change with flooding, etc., etc. So yes, there is brand new challenges with regards these matrices. Then they are primary processed, for example. So if you get harvested in the field, then they're primary processed. They undergo some form of washing, cleaning, sanitation. There may be IQF before they arrive at the retailer or before they arrive at the next customer. So for sure, this new, let's say, reality has to be taken account of when we think of our hazard analysis. So that's why HACCP is always I always view HACCP as being a very dynamic tool, because your hazard, your pathogen, and your material combination will change quite often.
Thank you, John. Probably the last question from today, because we are running out of time, honestly, guys. The question is coming from Elena Ageva. If there is evidence of the effect of biofilms on the results of pathogen research in the product environment.
I'm not sure what the question was again. Is there evidence of the effect of
Is
biofilms?
there? Yeah.
Well, biofilms are, let's say, a recognized phenomenon, in the food industry, and some let's say processing environments or processes are more vulnerable than others depending on the matrix you're using. For example, in the dairy industry, we get biofilms can form quite regularly, and this can be a challenge because even when you do your cleaning, and you're sanitizing, you do not necessarily remove your biofilm. And this is why I always say validation of cleaning and sanitation is so important, and verifying that your sanitation works on a regular basis, or monitoring on a regular basis that it works. Because as a biofilm builds, your cleaning may become less effective. So it is important to recognize this. However, what we have seen more recently, and I'll come back to the metagenomics topic, is that some of the cleaning agents now, they move, instead of chemicals, they're also incorporating enzymes into their cleaning tools. So enzyme cleaning is now a recognized, say, recognized tool for as part of your cleaning regime, and that is enzymes are specifically targeting biofilms, because biofilms will be a protein, carbohydrate, polysaccharide type of mix, along with microorganisms, of course. But by actually including enzymes, you can digest away your biofilms. So if you suspect you have biofilm, then this can be sort of a way of trying to remove it, because otherwise it can bring you problems, especially in various food manufacturing facilities. But if I go back to metagenomics, and someone asked earlier about the use of metagenomics, where I've actually seen is where people have been trying to validate enzymatic cleaning. So they clean a line with normal chemicals and they think it's clean. So they measure the clean water rinsing at the end, and it's clean. They then use an enzyme clean, and then they look at the metagenomic profile of the water that comes out after the enzymatic clean, and it's remarkable. You think you have clean water by a normal clean, you add an enzyme, and you enzyme cleaning, and suddenly when you look at the water, you can see lots of microorganisms present by metagenomics. So it is proving that the enzymes did something beyond what the chemicals were doing in terms of cleaning. So this is actually a nice use of metagenomics, which actually sort of shows you that by enzyme cleaning, you can actually remove a lot more microorganisms than you could with normal chemicals. So a lot of the cleaning manufacture of cleaning agents are looking in this direction now as well, I see. But metagenomics might help to validate enzymatic cleaning, that it works.
Thank you, John. And at the end, I would ask you to give us like a brief summary. Uh, what are the biggest challenges in the food industry now, on your opinion, which faces today regarding consumer trust and safety in general?
The biggest challenge is the lack of microbiologists. So anyone out there that's a microbiologist, here, praise to the microbiologists, because this will not disappear. Challenges around microbiology will never disappear in the food industry. So this is an important part that we have a good stream and we have good educators in academia that is educating the next generation of food safety microbiologists. This is extremely important because the food industry may not be the most attractive perhaps for graduates, and I know this from my own kids. None of them want to do food safety microbiology. They want to do nutrition if they're in science. So it's important that we have people that follow this as a career and develop expertise. The big challenges is, well, it's in a number of fronts. Firstly, I would say the analytics are moving faster than the regulators, and you have then other groups, for example, like NGOs, who will perhaps do surveys more so on the chemical side than the microbiology side, which also puts a demand from the public to be able to produce safe food. And some people still think that all food is sterile, and this is risk communication is a big weakness on all our parts, be it the regulator, be it the food industry, be it academia, to be able to communicate to people that there's a residual risk, associated with all foods. But going back to my point about the methods, if I take something like whole genome sequencing, if I take, you could serve 12 million servings of food, you could release it according to the highest specification you could think of and regulatory compliant, and you could get three people who could get ill from consuming among that 12 billion servings or 12 million servings, and those are related by whole genome sequencing. How do you manage that as a food industry? Because from a regulator's perspective, and that's what I say. Sometimes the technology, the analytical sensitivity, is actually moving faster than what the regulators can regulate. So that's a little bit of a challenge for us all.
Thank you so much, John, and thank you everyone for attending this webinar. It was quite an active session, and I see your reactions. Everyone is super excited. And John, I'm using the opportunity now to invite you for our next webinar to talk about digitalization.
Mm,
Definitely,
yes.
everyone will be happy to hear it from you. And you guys, just drop me a message if you want to get this presentation. I hope John doesn't mind, right?
No, no, it's
Yeah,
okay. I share.
definitely. The recording will be available on our website and in LinkedIn page, and plus you will get it privately to your emails. And just have an amazing day. Stay tuned for future speakers, and see you later. Bye.
Thank you all very much. Bye.